So far, we've learned what a complex number is, we've even learned how to graph it, and we learned how to add, subtract, and multiply it. And where I left off in the last video is how do we divide two complex numbers? So I said, let's say I have one complex number, z1, and that equals a plus bi, and I want to divide that by z2, which is c plus di. So let me ask you a question, and I touched on this in the last video, and let me do it in a different color here. We know that a plus b times a minus b is equal to a squared minus b squared, and you can multiply it out if in case you're not sure. You remember it's just a times a plus b times a plus minus a times b minus plus a times a, and you'll get this. I don't know if I said that right, but you know how to do this. Anyway, there's a review if you need to do it. So given that, what is c plus d? What happens if we do something very similar with a complex number? If we say c plus di times c minus di. Well, in this case, a is c and b is di, right? So this is just going to be equal to c squared minus di squared. Di squared. And that equals c squared minus d squared I squared. And that equals c squared minus d squared. And I squared is -1, right? So this is going to be multiplied by -1, so it cancels out this negative. So you get c squared plus d squared. That's interesting. When I multiply a complex number times this other number, which is very similar to it, but it's kind of the imaginary part goes in the other direction. When I multiply the two, I get a completely real number. All of the i's disappear. And in general, this number, if we call this z, well, in our example, this was z2. So if we say that z2 equals c plus di, the quantity c minus di is called its conjugate. And that's just good terminology, you know. And the sign for conjugate is that line over the top. So the conjugate of z2 is c minus di. Or you could say the conjugate of c minus di is equal to c plus di. Or you could say it the other way around. The conjugate of c plus di is equal to c minus di. And notice, we're just switching the direction in the imaginary, along the imaginary axis when we take the conjugate of something. With that said, let me erase that and go back to our original problem, because the conjugate is the tool we're going to use to divide this. So we know when we multiply an imaginary number times its conjugate, we get a real number. So, and we know also if we can multiply anything by 1 and we get the same number. So let's multiply the numerator and denominator of this expression by the conjugate of the denominator. So let me do that. So the conjugate of the denominator is going to be c minus di. So c minus di over c minus di, right? This was c plus di, so this is its conjugate. And so what do we get? So in the numerator, we get AC, I don't want to run out of space, I always do, AC, so A times C, minus ADI, minus ADI, and these I's keep looking funny, this is an I too, plus BCI, plus BCI, and then the last term, we have a plus b minus b, so it's minus bdi squared. Minus bdi squared. All of that. And when this is a plus b times a minus b, so it's equal to a squared minus b squared. So this is going to be equal to, and this will become second nature to you after a while, but you might want to just multiply it out. This equals c squared plus d squared. And don't take my word for it. Actually, algebraically multiply this out and just realize you can only add real parts to real parts and imaginary parts to imaginary parts. So let me simplify that. That equals, let's see, the real parts, this is real, AC, and this is minus BDI squared. So the I squared is minus 1, so it switches the sign here, so it becomes plus BD, and we can get rid of the I. So the real parts are AC plus BD, that's that and that. And then the imaginary parts are plus, this one's positive, so I'll put that one first, BC minus AD I. All of that over C squared plus D squared. And that still might not look like a complex number to you, but then we can separate them out, and we could say, well, that equals AC plus BD over C squared plus D squared, and that's the real part, plus BC minus AD over C squared plus D squared, and that times I, and that's the imaginary part. So you can't merge when you're adding and subtracting the real part to the imaginary part, but you can most definitely scale an imaginary number by a real number, and that's essentially what we're doing. We're multiplying 1 over C squared plus D squared times this. So division might seem a little complicated when I write it all in variables, but let me give you an example, and you will hopefully see that with real numbers, and well, not real numbers, with actual numbers. I should be careful with what I say. Let's say I have 1 plus 2i, and I want to divide that by, I don't know, let's divide it by, I'm going to pick a random number, 2 plus 3i. And so what do? We multiply it times the conjugate of the denominator, 2 minus 3i over itself, right? Because then we're not changing the number. This is just 1. This simplifies to 1. It equals. The bottom, we can multiply it out, but hopefully it's second nature to you. It equals 4 plus 9, right? And because that's just a squared plus b squared, right? Well, I mean, it's a squared minus b squared, but then the i's when you multiply them become a negative number. Try it out if you don't believe me. And then the top, we get 1 times 2 is 2. 1 times minus 3i is minus 3i. Then you have 2i times 2, which is plus 4i. And then you have 2i times minus 3i. So that's minus 6i squared. Well, what does I squared equal? That equals negative 1. So negative 1 times negative 6. Get rid of the I squared, and this becomes a positive. So then what are our real parts? Our real parts are 2 and 6. So 2 plus 6 is 8. And what are our imaginary parts? Minus 3i plus 4i. So that's just plus 1i, right? Minus 3 plus 4 is positive 1. So it's just plus 1i over 13. Or we could write that as if we wanted to write it in kind of the traditional complex form, is 8 over 13 plus 1 over 13i. So when I divided by one complex number by another, I got another complex number. And an interesting exercise for you to do is pick some random complex numbers, plot them out on the complex plane, and see what happens when you multiply them, when you divide them, when you add them, when you subtract them, and when you scale them, or when you take the conjugate, and that'll give you a better intuition of what's going on with these numbers. Anyway, I will see you in the next video.